We are going to skip limits of piecewise functions for now, and we'll come back to it in a different lesson. So right now we're going to focus on finding the limits of trig functions. So for these trig functions, it's important that we know some of our trig identities that we've learned in the past. So if we take a look at the first example, finding the limit as x approaches 0 of tan x over sine x, we cannot plug in 0 the way that this is written because the sine of 0 equals 0. So we would get a 0 in the denominator. But we do remember that the tangent of x is the same as sine x over cosine x. So we're going to rewrite this as the limit as x approaches 0 of sine x over cosine x times 1 over sine x. So we'll take this sine x that was in the denominator and write him as 1 over sine x. So now this is good because we can cancel out our sine x's. So we're left with the limit as x approaches 0 of 1 over cosine x. And the good news about this is that if we take the cosine of 0, we get 1. So we can take 0 and plug it in at this point. So the cosine of 0 is 1, so 1 over 1 would give the answer of 1. Moving on down to our two trig theorems. So our first theorem is the limit of sine x over x as x approaches 0. This equals 1. So this is just a theorem that you need to memorize, that the limit as x approaches 0 of sine x over x equals 1. It also would be true for the limit as x approaches 0 of x over sine x. This also equals 1. So if you flip sine x over x, it still equals 1. This theorem is also true if you have a situation like this. The limit as x approaches 0 of sine 2x over 2x. This also equals 1. This would be also true if we had sine 3x over 3x, or if we had 4x over the sine of 4x. This would all give us a value of 1. So as long as this value matches up with this value, we're going to have a limit of 1. Moving on to the next theorem, we have the limit as x approaches 0 of 1 minus cosine x over x. This equals 0. And this is the only part of the theorem that you need to memorize. Okay, so let's use these two theorems for the following examples. So let's take a look at our first one. The limit as x goes to 0 of sine x over 4x. So we kind of have an extra 4 in the denominator that we don't need. So what we're going to do is rewrite this as the limit as x approaches 0 of 1/4 times sine x over x. So now that is the exact same thing that's right here. It's just written a little differently. And we want to rewrite it like this because what we can do now is, using our properties of limits, we can pull out a 1/4 since it's a constant. So we have 1/4 times the limit as x approaches 0 of sine x over x. And due to our theorem, we know that this portion equals 1. So now we have 1/4 times 1, which just equals 1/4. When you're doing these problems, it's very important that you are illustrating the properties and that you're also showing the theorem. So I should see the function first broken up, and then the 1/4 pulled out to illustrate the properties of limits, And then I should see that the limit as x approaches 0 of sine x over x actually equals 1. Moving on to the next example, we have the limit as x approaches 0 of sine 4x over a regular x. So now it would be super awesome if instead of a regular x, we actually had a 4x, because then we know that this would equal 1. But we don't. But that's okay, because we can give it a 4x in the denominator by simply multiplying by 4 over 4. So we end up with the limit as x approaches 0 of 4 times sine 4x over 4x. So now we know that this portion is going to equal 1, but we still have to break up the limits using the property of limits. So we're going to put the 4 up front. And now we can say that this portion equals 1. So we have 4 times 1, which equals 4. Moving on down to our next examples, we have the limit as x approaches 0 of 1 minus cosine squared x over x. Now this looks very similar to our theorem, but it's not exactly it. So we can't just say that this thing equals 0. So what we have to do is think about maybe another way that we can write 1 minus cosine squared x. We do know that 1 minus cosine squared x equals sine squared x, so maybe we can work with that. So we're going to rewrite this as the limit as x approaches 0 of sine squared x over x. Now this also looks pretty similar to our other theorem, but it's not exactly it. So we're going to rewrite it so we can get that exact theorem. So sine squared x is just sine x times sine x, so I'm going to write this as sine x times sine x over x. And now we're pretty close to having our theorem. Unlike the 4, we cannot take the sine x and pull it out in front because sine x is actually a function. But what we can do is we can rewrite this as the limit as x approaches 0 of sine x times the limit as x approaches 0 of sine x over x. That is one of our properties of limits, is that we can break up f of x times g of x as the limit of f of x times the limit of g of x. So now we can simply just take 0 and plug it in for the first portion. And then the second portion is our theorem, so we know that that equals 1. And we know that the sine of 0 is 0. So 0 times 1 equals 0. All right, moving on down to our next example. So this example gets pretty complicated. We have sine of 3x over sine of 2x. Unfortunately, this kind of looks like our theorem, but not exactly. It would be great if we were working with sine 3x over 3x, because we know that that would equal 1. It would also be great if we were working with 2x over the sine of 2x, because that would also equal 1. So we're going to kind of use that strategy to help us break up this limit and hopefully get a couple theorems going for us. So the first thing we're going to do is rewrite this as the limit as x approaches 0 of the sine of 3x times 1 over the sine of 2x. So now what I want to do is give this term a 3x on the bottom. So I'm going to multiply by 3x over 3x. And then I also want to give this other term a 2x on the top. So I'm going to multiply by 2x over 2x. Now I'm going to be a little tricky on how I rewrite all of these terms. So first I'm going to have the limit as x approaches 0 of the sine of 3x over 3x. So I'm basically taking this 3x and putting him in the denominator. And I'm also going to have 2x over sine 2x. So I'm taking this 2x and putting him in the denominator. But what that leaves me is this 3x in the numerator and this 2x in the denominator. So I'm just going to write them separately over here. Okay, so now let's use the properties of limits to further break up this function. So I have the limit as x approaches 0 of sine 3x over 3x times the limit as x approaches 0 of 2x over sine 2x times the limit as x approaches 0 of 3x over 2x. Okay, so now using our theorems, we know that our first term equals 1, our second term equals 1, and our third term, we can't plug in 0 the way it is because we'll get a 0 in the denominator. However, our x in the numerator and our x in the denominator cancel. So we just have 3 halves. So our final answer, 1 times 1 times 3 halves, is 3 halves.